We're going to use the examples from our textbook. I'm going to be going over a couple fixed effects models and trying to point out, at least in the initial model, where some of those things might go in our templates and our outputs from our textbook. So our example from our book uses the independent variable of type of sport, and our dependent variable is distress. It's a self-report of psychological distress. Let's go to our data view. All right, you'll see I have our second variable independent variable we'll come back to when we do a factorial model. For now, let's just do a one-factor ANOVA fixed effects model running through the example from our textbook. So in our book, our analysis that we examined is a general linear model. It's an analysis of variance. We're going to put in to our dependent variable list psychological distress, and we're going to use type of sport as our predictor here as a fixed factor. Later on in the semester, we'll add some random factors, and later on, either in this video or a series of videos, we'll add a second factor in to have two fixed factors in our model. Let's go ahead and go through, assuming we're doing the one-way analysis of variance. Let's select a couple options. I'll kind of go down this list in order. Plots, I always like to plot my data, so I'm going to plot sport. I select plot, put it in the horizontal axis, and select add. Now I'll be able to see what those four levels of sport look like as a graph. Usually if I can't see a difference, I tend not to believe it, so I really like to see the difference in the data. All right, next let's do some post hocs. Yeah, let's do a post hoc. Let's do Tukey's test as the most frequent one we've done and we've talked about, so I'll go ahead and click Tukey's test. This will be from chapter 2 in our textbook. I'm going to click continue for post hoc comparisons. There we go. I'll mention here, and I'll mention as later on I've mentioned in class too, SPSS does Tukey's test slightly differently. They use what's called the harmonic mean. In our class and any practices we do for Tukey's, we're using the standardized range statistic. So our denominator will be slightly different, but that's okay. We'll take a look at what is produced here in SPSS. So let's go to our expected means here, and we'll go ahead and select both overall and sport to display the means. For now, we're not going to select compare effects since we're doing post hoc test. And for our residuals, we want to save unstandardized residuals, and we do this for some of our tests later on when we explore some of our assumptions of our statistics. So let's go ahead and continue. And then finally, I'm going to click Options. Under Options, I'm going to select Descriptive Statistics, and I'd like some estimates of our effect size, like eta and partial eta squared. Observed power. I want to know what my Levene's test, my homogeneity test, and it's nice to see the spread versus level plot. Let's go ahead and click Continue. All right. Now I'm going to click OK. And there we go. Now my output might look a little differently than yours. I've set my output up to be closer to APA format. You'll see if you go up to Edit and go down to Options, and we go over to Pivot Tables, you'll see I have APA Times Roman 12-point font selected. So it's giving me some default tables and figures that are going to look closer. I still would probably go through and have to edit some of these tables, but they're pretty close. They're a very good start. So let's go through and see what we have. We have overall, we see that we have 9. We have 8 persons in each group, which is what we're supposed to have. We can see under our descriptives the means of each for movement, target, fielding, and territory, and then the overall mean as well as standard deviations. Just by eyeballing the standard deviations, by seeing their relative size toward each other, I kind of know that the Levene's test is going to be fine, that they're going to be relatively the same size. And we can see that we do not have significance here for our f-test, which means that we can assume that there's equal variances amongst our different groups. Next up, we have our analysis of variance table, and I'll mention a few things here. From class, we did some of the direct computation of analysis of variance. We understood sums of squares, and from those we used our sums of squares and divided the appropriate degrees of freedom. Sums of squares divided by degrees of freedom are our mean squares. And then the f-test is a ratio of the mean square between over the mean square within. Or in this case, it's the mean square of effect. And we call our effect in this case, instead of generically calling it A, we're calling it sport. So that's the type of sport. And our within is error. It's our error term. So within and error, we often hear synonymous toward each other. So that within groups means squares, it tells us about the observations about how within the groups how our data vary, and sports tells us between groups how those would vary. So we have an overall. Now let me go things that are important. We can sort of not worry right now about corrected or intercept. We can focus on our sport, our error, and our corrected total. So we see sport, that's our main effect. We go over, we see 3 degrees of freedom. We had 4 groups. 4 minus 1 is 3 degrees of freedom. We've calculated our mean squared. And our f-test here is 6.8. That f is the ratio of the mean squares of 246.198 divided by 36.112. And that's the f ratio. And we test that for significance. Here, SPSS just defaults it. We don't have to go to any of the tables in the back of our book. We could do so as well, but for now, it just gives us the default. We would say that this is less that our F ratio, our F test is computed, and it is significant, is less than 0.001. We also automatically have eta squared calculated here for us. In this case, our eta squared, remember eta squared is sums of squares between over sums of squares total. So sums of squares between in this case was 738. Sums of squares total is that for the corrected model is 1749. We take that, we get that ratio, and we get 0.422. We also asked for power. Remember, observed power is our ability to detect a difference if it really exists. Here's power here, it's 0.956. That means we had almost a 95.5% chance of finding a difference if it really existed. Or if, in this way of saying, we had a chance of rejecting the null if we were indeed supposed to. So this is really pretty strong power for this model. So that's our general analysis of variance table that we've worked on in class. Here are our estimated marginal means. These are the means. So this first one is the overall grand mean. So we have a 18.406. What I like about this gives you the error confidence bound around it. So we can see that it ranges between 16.2 and 20.5. So if we were to, that 95% confidence interval is around this grand mean of 18.4. And then the same thing here for each sport type. We can see, go through the marginal mean after computation, and each one of those mean values, the standard error, and the lower and upper boundaries around those means. All right, let's go down. Hopefully get some post hoc tests. Oh, good. Here they are. Our multiple comparison tests. We asked for Tukey's test. So we'll just go over this now, and we'll take a look at our mean difference and our standard error. So one of the things I really like here in SPSS is that it computes the mean difference. The mean difference is just the difference literally between, in this case, the mean of movement and the mean of target. We get a negative 6.7. We'll see if we took the mean of target and the mean of movement, we get the reflex of that. It's positive instead of negative, 6.75. So these two are going to be the same analysis effectively. So we only want to, if we were reporting these, we'd only report half of these. We'd only report the positive or the negatives in one way or in one case or the other. So we can take a look both at whether or not that mean difference. We can look at the denominator. So when we think about all of our post hoc comparisons, all of our multiple comparison procedures, really they're all just some version of a t-test. And in class we talk about numerator and denominator. So really all of our tests are numerator, difference between some sort of mean, even if it's a conglomeration of other means. A denominator, we're calculating out a standard error. And then sometimes we adjust the table that we look at. And for here, we can just, in SPSS, take a look at the significance level. So we can see movement and target are not significant. And we can see movement versus fielding is, and so is movement versus territory. And we can go down and see where those significance lie. We come down to fielding versus movement and we realize, well, that's just the same thing as movement versus fielding. And let's see. Our mean squared error here of 36.11. If we go up here, we can see that that's just being pulled from an analysis of variance table. We're just using that mean squared error, that mean squared within, to calculate, and it's just coming from our table. So an SPSS is doing the same thing. So when you do these by hand, quote unquote, when you do these maybe in Excel or something for an assignment, you could be able to get the mean squared error from your table and do the same thing. The homogeneity test sort of says when they are not significant, we sort of couple those together. It's like a quick way of looking at our subtests, and we can see that movement and target weren't significantly different from each other. And then target, fielding, territory were not significantly different from each other. So as opposed to looking at things that are different, we're sort of nesting them together to see which subtests are relatively similar. And then, of course, we have our spread versus level plots. These are going to help us give us some sort of visualization when we think about the assumption. I tend to use these more when Levine's test is violated. It gives us an assumption of if there was a violation, what it might be, whether or not we should do something to the data. So if the assumption were not met for Levine's test, we might have to do something like take the square root of our data or do some sort of modification that way. But for now, we're going to leave that alone since our Levine's test was okay. And here we have the standard deviation spread and the variance spread. And finally, we have our estimated marginal means that we calculated. And we have them distributed, so we can kind of see that pattern. Not that there necessarily has to be an ordinal pattern here at all, but we can kind of see plotted out the difference below 12 here for movement, above here, 24 here for territory. So it kind of gives us a very quick idea that when we say our F test was significant, we get a visualization. We can kind of see these two are hanging out pretty close to each other. So we can kind of use this visualization of our profile plots to support those multiple comparison procedures that we saw earlier. We see a difference between movement and fielding and territory. And we can see down here, we see a difference between movement and fielding and territory. All right, I had also asked SPSS to give me residuals. So these residuals we can use. So these are the difference between the score on the dependent variable and the mean within the groups. So we can see that our residuals we just basically compute them by subtracting the group mean from the dependent variable value for each one. So we could go back and look and see in our data earlier on, our mean of movement was 11.125. So we would be taking that value, 11.125, and subtracting it from the stress, and we end up with S value of 3.87. So we do that for each individual, go through them, but we don't do it. SPSS in this case does it for us. So we can take, one of the reasons we want to plot this, one of the reasons we take the residuals is sort of to take out the weight, the value of the group mean, and then we can look to see whether or not, in this case, we can start off by looking at whether or not some of the assumptions of normality are met. So let's go up to Analyze and Descriptives, and we'll do an exploration here. And we will put our residual for distress in as our dependent list for now. And under plots, I'm going to ask for histograms and normal plots and hit continue. I think under options are just missing values for our data. And first, I'm going to just select this and run this by itself first without the factor list. I'll go ahead and do that. And I get some pretty good information here. I get the overall mean, which we expect to see as 0 because we've removed that effect from the model. Our kurtosis and skew are reported here as negative 0.239. Kurtosis is -1. Sometimes people just do, for normality, they break them out by groups. They don't necessarily do the residuals. I'm really not against doing it that way, but this way, when you do the residual, you can start off by doing the base residual. And the base residual is, I just mean the overall variable residual. Let's take a peek down here at Shapiro-Wilks test. So when we do the Shapiro-Wilks test, we see that that is also not significant. That is another measure of normality. And I'm going to jump, since I mentioned by groups, go back to descriptives, and we can take a look at within each group. So we were looking at our residual for distress, and we initially looked at type of sport. So we can do all those same things we did here, and we can do that by type of sport. So now we can have it broken out. Here we go. We get those data points, our skew and kurtosis, 0.449 and 0.575. You can take a peek at your template and examples in the textbook and see that those match. We also can see that our significance levels are not significant for the Shapiro-Wilks. Every once in a while, one of the groups might be off for normality. We may have to check it. We have to consider transformations. For normality, though, is you know, often we're a little robust here. So, but we're fine in this model. There's no reason to consider that. And then we have some of our charts that just give us visualizations. Catch up a little. Here we go. Expected normality is the line. We look at our, in this case, our QQ plots. Basically, we're looking to see whether or not the expected is different than the observed. And we can see these data points match pretty well. I guess I should specify what I mean by pretty well is that when I'm looking at those points, the points that fall close to the line suggest that there's evidence of normality. When they fall real far from the line, we would expect there to be, there could be a problem with normality. We're going to go and do some of the test of independence. So actually, we've taken a look at some of these charts, including things like, we can take a look at our other charts and link them up to the textbook, but mostly we've seen the test for homogeneity of variance. We've taken a look at our normality. These are just different box plots by different groups. We can see how those are laid out for the residual for distress. And let's go ahead and I'll go back to our data. I like to do it from this perspective and graph. And we're going to look for some of the issues around independence. Now, I'm a big proponent of logical independence that I've mentioned in class, and statistical independence where you're able to, you know, maybe you can't randomly select people, but you can randomly assign them different groups. Logical arguments are often constructed around people being not being assigned to groups, but that intact groups somehow are similar. And we can also support that with our data. So for example, we might want to do an analysis here. I'll go to under legacy. We're going to go to a simple scatter plot here. Here's scatter plots. Let's select simple scatter plot. And on the y-axis, we're going to put our residual here. And on the x-axis, we'll put type of sport. And let's see here. There we go. Here is our residual, our graph of residuals. We could put a line through here like your textbook to look around 0. Really what we're doing is we're looking to see that points in general randomly fall above and below the reference line. The reference line would be a point that I could put through the middle here at 0. Let's see. There we go. Now we can see things seem to be randomly scattered above and below. I will just show briefly our template, some of the points that we've been going to go sort of backwards here. I know this video getting a little bit long, but I just figured I'd go a little back and forth here. We can see the Shapiro-Wilks test is reported. Some of these things that were reported in R, we're not going to go over here. Just focusing on those elements that are from SPSS. Same with your homework assignments. Those things that are from SPSS are required. Those things that are from R were optional. It might just be useful to take a peek at, let's see, our F test. Well, we kind of remember that was 6.8. We'll see how F is italicized. Our Greek letters, our Roman letters here are all going to be italicized. You'll see our Greek letters are not italicized. So we can go back, and I had started a little search here for our, here we go. We see that our F test was 6.8. It was significant. Here we just place that in here with appropriate degrees of freedom. Remember, degrees of freedom numerator over degrees of freedom denominator. Degrees of freedom between, which was 3, and over degrees of freedom within. Let me go back to SPSS. We can see we just pulled those right from our model, 3 and 28. The Tukey's test, we see that we reported which of those were significant and at what level. And some of the means and standard deviations were reported. I mean, those are just literally the means and standard deviations from our descriptive statistics. Levine's test that was reported is from here as well. See Levine's test, 0.451. And here, the Levine's test was reported up here as 0.905 with p equals 0.451. We see that matches our outcome. So I just want to sort of show you 0.905, sorry, and 0.451, that I'm just taking those elements and placing them. All of our preliminary template here that we pulled from our textbook. This template is giving us our normality, evidence for homogeneity of variance, and that we explored the data looking at residuals for independence. And then here we're placing our F test, our general means we'll have reported for our, we'll have merged our template for multiple comparison procedures. So we'll also be mentioning things about our actual Tukey's test and reporting those actual values. Last thing I'll point out is that we also, well, last two things, we reported our effect size. Now this effect actually had to be hand calculated. It was if you wanted omega, but if you just wanted to report eta squared, you could have reported that directly from SPSS. So eta squared effect is reported directly, 0.422, but in our textbook we'd have to do that mathematical transformation for if we wanted to report omega squared or partial omega squared, as we'll see in another video. And also power should be here. Our power that's reported is quite high, and we see that's right here of 0.956, and we calculated our power of 0.956. So I don't want to go through every element of this, and although I just went through most of those, but our assignment and learning how to take our data, conduct an analysis of variance, review the assumptions, and place them into sort of a template style format that's matching our textbook. This really gets us pretty far down the road into producing our results section. So I just wanted to give you that example. I will not do, and this video has already gotten a little long, so we'll just kind of end this video here, and we'll worry about adding a second factor for the factorial model into our next video.